Hello physics students. Welcome to Spark Lab 2, Uniform Acceleration. So at this point, you should have already printed out the data sheets from page 3 on to page 5. Pages 1 and 2, the instructions, you don't have to print out if you don't want to. All right, so what are we going to do in this lab? We're going to do the same kind of analysis that we did in Spark Lab 1. We're going to create a spark tape and analyze it, but in Spark Lab 1, we looked at something going at a constant speed. In this experiment, we're going to look at something accelerating. And the easiest way to make something accelerate is simply to drop something. Then the acceleration, because of the Earth's pull downward, will be 9.8, or it should be 9.8. Okay, unless there's some kind of air resistance or something. So that's what we're going to do. We're going to drop something, make a spark tape out of it, and then the learning goals will be pretty much the same learning goals as Spark Lab 1, but for acceleration. So, for example, you will learn the shapes of the distance versus time and the velocity versus time graphs for an object with uniform acceleration. Something dropped, 9.8, uniform acceleration. You're going to learn the slope of a displacement versus time graph is equal to the velocity of the object. And you're going to learn that the slope of a velocity versus time graph is equal to the acceleration of the object. The material is very similar. We're going to use a spark timer, which I've mounted here to the wall with a couple clamps, 2 pieces of spark tape, 1 for each lab partner, a ruler or meter stick to measure the spark tape, and a weight to be dropped, and an old book to cushion the impact. The weight to be dropped, it's an old fishing weight made of lead, okay? This is a big fishing weight, probably for ocean fishing. And what you do is, oh, hey, I'm doing something here. What you do is you tape this tape onto this spark tape onto the lead weight, and you can see that basically the lead weight is supported by the spark tape. I'm going to feed that through the timer, and then I'm going to drop it. And as it drops, the spark marks are going to make a pattern that's consistent with something accelerating at 9.8. Okay? Now, the thing is, you have to be careful when you drop this. You can't let it drag through your fingers. What you have to do is you have to try and open your fingers as quickly as possible so that you don't get something less than 9.8 because of the drag. It opens and it falls 9.8. So that's the goal. All right, so let me feed this through the timer. I'm going to hold this. I'm going to turn the timer on and drop the weight to generate the pattern that we're looking for. All right, shut the timer off. And there is the tape, okay? So what I'm going to do to show you the pattern is now I'm going to switch to my desk cam view, okay? So hold on a minute.
Okay, welcome back. So at this point, we've done all this procedure through step 8. Step 8 was for me to inspect your spark tape to make sure it's suitable for analysis, but I've already done that because I'm going to provide you with a spark tape. And where you're going to find the spark tape, there will be a page in the stream that will have images of multiple spark tapes. Find the one with your name on it, print out that sheet, cut out the spark tape with scissors, and then that's what you're going to analyze. And what you should see is a spark tape that looks like this. Now, what I've done is I've gone ahead and labeled the dots as we did in the previous lab, as instructed in step 9 from dot 0 to dot 10. And what we could see already is that it looks different than the tape from Spark Lab 1, which looks like this. Spark Lab 1, the spaces were all even. So what that meant, and the reason for that is because the object, the dune buggy, was going at a constant speed. So if we do distance over time for any pair of sparks, we measure that distance and we divide by the time from here to here, which is 1/60th of a second, we get a certain number for the speed. If we do that anywhere else, we have the same distance over the same 1/60th of a second because the dots are evenly spaced. We get the same v over here as we did over there. Speed v is constant throughout because the spacing is even. Whereas over here, we could see that the v equals d over t. I have one distance here, and over here I've got another distance which is larger for the same time from one spark to the next. That means with a larger d, for the same time, we have more velocity here. So we could see from the spacing that the object is speeding up, okay? So what we're going to do now is step 10, okay? So step 10, we're going to calculate what that acceleration actually is. And it tells you to remember the time between each pair of marks is 1/60th second. First, we're going to calculate the speed between dots 3 and 4, and then the speed between 5 or 6, and we should see two different answers because the weight that we dropped was speeding up. So I've taped this spark tape on this page only because spark tape, you're constantly fighting it, it rolls itself up. So I did that here. Don't tape yours down because yours will be a regular piece of paper, and the tape goes actually on the next page. So again, don't tape yours down here, but so we're going to calculate the speed between dots 3 and 4 here, and then the speed between 5 and 6 here. So as always, how do you calculate things? Well, you go to the reference table, you find the appropriate formula. This is page 6, the back cover of the reference table. Here's v equals d over t. You must start every calculation with a formula. So there is my formula. Now I'm going to plug in numbers. So I'm going to measure between dots 3 and 4 how far apart these dots are. So here we are, 3 and 4. Looks like 1.06. Again, remember that when, let me move that up a little bit. So when you're making a measurement with a ruler, you have to estimate the last digit. So this is somewhere between this dot 4 is between 1.0 and 1.1, a little bit beyond the halfway point, which makes 1.06 centimeters. Again, you might say 1.07, that's okay, but you do have to estimate that last digit. I'm going to call it 1.06. That's what goes in the top here, 1.06 centimeters, okay, there. And then the time from one spark to another is always 1/60th of a second. So the time from here to here, 1/60th. I plug that in with the units, right? And I'm going to go ahead and calculate. Again, you're going to have your own measurement here, right? Because you're going to have your own tape. 1.06 divided by 1 over 60, and that gives me 63.6. So I will write that 63.6. Now the units are in centimeters per second, so I will make sure I label that. So this is V, maybe I'll call this V initial. Now, between 5 and 6, I got to repeat the same process over here. So I have the same formula, V equals D over T, but now I have to measure between 5 and 6. So let's see, I've got 1.6, well, looks like to me right on the dot. So remember, if a point falls right on the dot, we call that 1.60. We put a 0 at the end. Always need to the hundredths place, even if it's on the dot, you still put that 0. Centimeters, and the time between dots 5 and 6 is still 1/60th of a second. So I divide those out. $96, okay, so there it is. So that I'll say V final. Remember, you're going to have a different number here. You're going to have a different number here because you're going to have a different tape, okay? So you're not copying, you're just following me along and doing what I'm doing, okay, as you go along. Now, the next thing, step 10C. 10C says calculate the acceleration over the interval. Hint, the time you plug into the acceleration equation is not 1/60 of a second. We'll talk about that in a second. So, how do we calculate acceleration? Always go to the reference table, find a formula. There it is. A is delta V over T. Now, remember, delta of anything is always final minus initial. So what I have here for a final is I've got my 96 right here and my initial of 63.6. So final is 96. I could put 0.0 meters per, or sorry, centimeters per second. (96 centimeters per second) minus the 63.6 centimeters per second all over. Now, the time is not 1/60th of a second. Why not? Okay, well, this 63.6 is the average speed between dots 3 and dots 4. So if I go here, and I ask you, when is the speed 63.6? If this is accelerating, and this is the average between these 2 points, do you suppose that 63.6 happens right at the start of the interval, right at the end, or somewhere in the middle? And the average, of course, is right in the middle. So this velocity occurred right there, in the midpoint. And this speed right here, 96, is the average speed between dots 5 and 6. Did that occur at the middle, at the beginning of the interval, at the end, or somewhere in the middle? And if you said somewhere in the middle, then you're correct again. So, how much time is between this line and this line? This isn't 1, it's half. Here's one interval, so here's half an interval. Here's a full interval, so we've got 0.5 plus 1, which is 1.5, and then another half of an interval. So 1.5 plus 0.5 is 2/60ths of a second between these two lines. In other words, between this velocity and that velocity is 2/60ths of a second. So now I'm going to go ahead and make that calculation. So I'll use some parentheses, 96 minus 63.6 divided by, again parentheses, 2 divided by 60, enter, and I get 972. Now, what are the units? Well, you might say acceleration is always meters per second squared. Well, usually. But look what we have here. We have centimeters per second on top, and we're dividing by seconds. What that gives us is centimeters per second squared. Okay? Now, step 10D says, calculate the percent error between the experimental value determined in step 2C and the accepted value of 981 centimeters per second squared. Okay? Because usually we say 9.8, right? But that's in meters per second squared. If we stay in centimeters, 9.8 is 980. And since it's technically 9.81, it's 981. So what we could do here is a percent error. And the percent error formula is the accepted value minus the experiment over the accepted value times 100%. So what I have is the accepted value is 981 centimeters per second squared minus 972 is my experiment, all over 981 absolute value times 100%. So I could enter that like this. Let's see. 981 minus 972 divided by 981, oops, I could hit enter, and multiply that by 100, and I get 0.9% error, which is really good. Okay. And with percent error, you don't have to have a lot of sig figs, you know, that's good enough. You could put it 0.92 maybe if you wanted to. So that's the first page, okay? Call your teacher over to check your calculations. Well, we can't do that because we are in different locations. You're at home and I'm at home, so can't do that. Okay, so next thing, we move on, and step 11, next, fill in the position column in your data sheet by measuring the total distance the car traveled at each time interval. Okay, so you do this, you fill in the data table, but first I'm going to move my spark tape. Now you never taped it down, so you would just go here to the next page, and notice it says affix your spark tape to this box. So you would do something like this, okay? Tape it on. Actually, yeah, I think that's how we'll do it. You'll have to tape it on because you're going to print out on a sheet. Now, this data table, it looks familiar, like in Spark Lab 1, which, where did I put that lab sheet? Okay, so remember in Spark Lab 1, the way we filled this this data table in, the same exact procedure. I'm not going to go over that again because you could go back to the video that I created for Spark Lab 1. And in fact, what I could do is I could, in this Google Classroom stream, I'll put a link to it in YouTube, not through Edpuzzle, because Edpuzzle doesn't allow you to fast forward. So I'll put it to YouTube, and then you could fast forward to the place where I fill in this data table. And so you'll see how to do it. The patterns will be different. These numbers will be small and get bigger and bigger because the spacing in the tape gets bigger and bigger. So these are going to increase and get bigger and bigger. They're not going to stay the same like in Spark Lab 1. The velocities are not going to stay constant because the falling weight will have a small velocity here and get bigger, bigger, bigger. But how you get these numbers is the same as Spark Lab 1. You're going to graph this, and instead of a straight line, you're going to see a different pattern. When you plot these points here, you will not use a ruler because you'll see that they are not a straight line. So you're just going to connect the dots here on this graph. But when you plot this graph, you're going to see that you could draw a best fit line here and calculate the slope of that. So you're going to calculate the slope here. Again, I don't have to go through the detail because you could go back to this video and get all that detail. And then finally, I just want to draw your attention to the questions at the end, which are very similar to Spark Lab 1 questions. Look only at your spark tape. How can you tell the object is accelerating? Explain carefully. It is not enough just to say the dots got further apart. Hint, dissect the formula that defines speed. So just like in Spark Lab 1, when you answer this question, you have to start with since V equals D over T. And then what you're going to do is talk about how the distance changes from one spark mark to the next as you go on with time. How does that numerator change? And how does the denominator change or stay constant from one spark to the next? So you're going to talk both about the numerator and the denominator here and come up with an explanation. Okay? The other questions, I don't think I need to say much more about, okay? Because I think you could figure them out, except down here, again, you're going to sketch the ideal distance versus time, velocity versus time, and acceleration versus time graphs for an object undergoing uniform acceleration. So over here, when something accelerates, you are going to draw what this should look like, the general pattern here, and the general pattern here. You could look at your notes, or you could go back and look at the graphs you actually created in the lab. Then in step 5, on the graphs you generated to answer 4, which is the ones I just had underneath, sketch the plots for a car moving with half the acceleration. Clearly label these points to distinguish them from your answers to question 4. So distance time graph for something accelerating here, and then with half the acceleration you plot it on the same graph and you label half A. Same here, you plot the original, you plot the half the acceleration, and you put half A next to the half acceleration, and same goes for acceleration. So that is the lab, and good luck with it. And if you have any questions, then certainly email me and I'll answer them as best as I can. So good luck with the lab.